let's understand what is mathematical induction. See, when we talk about mathematical induction, you need to understand what we do in this particular chapter more than what is mathematical induction. Because sometimes, rather than defining what the words represent, it's easier to say what that particular concept does. All right. See, here we mainly talk about how we prove couple of derivations or sequences, progression, something like this. Now, we'll take an example. Now, the logic behind this mathematical induction is very simple. Okay. So, we say that any particular type of a derivation you can say that that is given by some value p of x or p of n, whatever it might be. Okay, say p of n, because generally we say that nth term of a progression, right? So you can say n also, p of x, p of n, same way. Now, p of x, then what we do is we take x value as 1. That means we do p of 1. We prove or we show that p of 1 is true. Okay, we show that it's true. Next, what we'll do is we'll assume that p of k is also true. P of k is also true. Now, the next step is the crucial step. So, what we do is, see, if p of n is true, okay, suppose say p of n is true, then if you take p of k plus 1, it should be true. Suppose if it was not true for n number of terms, okay, assume if it is not true, then if you take a value, some value k plus 1, and if it doesn't satisfy, then you can say that p of n is not true, correct? So what we are doing is, you can also assume it to be like proving by contradiction, even though it's not. Okay, you can think of in that particular way. That is, we are taking, okay, so p of k plus 1, I'll assume it to be false. Okay, and then I'll show that it is true. All right, even though we are not doing that way, I'm just giving you an analogy. All right, so in this case, first you say p of 1 is true, you show it. Number you put 1 wherever you have the variable, and you can calculate. That's very, very simple. Then we assume it to be true for p of k, and we show that, okay, k into whatever. Then we prove that it is true for p of k plus 1. Because if it is true for p of k plus 1, it has to be true for any number n, correct? So that is what we are doing in this induction. Now I'll show you with an example, you will understand it even better. All right, see the example. Let's take an example of very simple one. Say 1 plus 2 plus 3 plus 4 till n number of terms is n into n plus 1 divided by 2. So I'll give you an example, prove that this is equal to this. Okay. So what we'll do, let p of n is equal to n into n plus 1 divided by 2. Okay. First step is what? Step 1. Step 1 is let n is equal to 1. First one. So p of 1 is equal to 1 into 1 plus 1 is 2 by 2, which is equal to 1. So what I want you to notice is see the first number, they are one and the same. So what we can say is this implies p of 1 is true. Remember, presentation in this particular chapter is extremely important. It's very, very important. All right. So in the second step, what we do? So in step 2, so we say that let p of k, which is equal to k into k plus 1 by 2, is also true. So p of k is also true. Now third step is very important. That is, you are proving p of k plus 1. Correct? So now step 3, we can say P of k plus 1. So P of k plus 1 becomes what? K plus 1 into k plus 1 divided by 2. So we need to prove that this is true, isn't it? This is the whole point of solving this particular problem. Alright, now P of k plus 1, let's start with the RHS. Alright, so taking RHS, now what do we have? K plus 1 into k plus 2 divided by 2, right? This is what we have. Now what you do, take the P of k value. So remember, this is the RHS of P of k plus 1, correct? So you can call this as equation number 1. Keep it aside. For now, keep it aside. So now what you do, start with P of k plus 1. Sorry, P of k. Sorry, not P of k plus 1. Start with P of k. So P of k becomes k into k plus 1 divided by 2, which is nothing but 1 plus 2 plus 3, so on and so forth till k. Make sense? Alright. Now what we are going to do? So for k into k plus 1 by 2, if you add k plus 1, now what is the meaning of this? This is, you see this particular sequence? For this, you are adding k plus 1, the next term. If P of k plus 1, you know what you're seeing, the step 3 part, what you're seeing P of k plus 1, if that is true, then whatever we are going to do in this particular step, that is 1 plus 2 plus 3 till k plus k plus 1. That means till k, you know it is k into k plus 1. You add an extra term to it. When you add an extra term, if the formula is correct, then when you add another number, the formula should still be correct, isn't it? Suppose if the formula was wrong, then obviously it's not going to work. This is what you are testing here. Till k, you know it is correct. So when you add k plus 1, will it still be correct? Will it still hold good? This is what you are trying to do in this particular formula. Alright? So in this case, k into k plus 1 by 2 is going to give you sum till k. So you add k plus 1. Now what do we do? Take LCM, normal LCM, nothing different. So you have k into k plus 1 plus 2 into k plus 1 whole divided by 2. Correct? So this is going to give us k square plus k plus 2k plus 2 whole divided by 2. Correct? So this is what you have. See, next thing what you can do, or see, rather than this, I would say that we'll take this particular equation itself. We can directly take k plus 1 as common. I mean, it's just going to be the same thing. I just expanded it. It's up to you. Okay, it's up to you. K plus 1, there only you can take common, or you can do it like this also. I mean, it's one and the same. Alright. So next what we can do here, if you do it the expanded form, then you will get k square plus 3k plus 2 divided by 2. Guys, if you split, it's going to give us the same thing anyway. Splitting the middle term types. So this is going to give us k square plus 2k plus k plus 2 by 2, or k into k plus 2 plus 1 into k plus 2 by 2. So this you can write this as k plus 1 into k plus 2 divided by 2, isn't it? Which you will get in the first part itself. Like what I told you, you can just take k plus 1 common, you will still get the same thing. Alright? Here, you will get this as k plus 1, and this you can write it as k plus 1 divided by 2. Right? K plus 1 is nothing but k plus 2. Now, call this as equation number 2. Remember equation 1 and equation 2? See this? Both equation 1 and equation 2 are one and the same, isn't it? So what we can conclude is that P of k plus k plus 1. So let me write it down now. What you get now is P of k plus k plus 1 is equal to P of k plus 1, isn't it? This is what we just proved right now. What does it indicate? That if you add an extra term, that's nothing but P of k plus 1 in the sense for that particular sequence or series, you add an extra term, the formula still holds good. This is nothing but the proving part that the formula holds good for any number or any value of n. So when you say this implies that P of k plus 1 is true, correct, for any value. So if P of k plus 1 is true, don't you think P of n should also be true? Because from P of k plus 1 only, P of n only we got P of k plus 1, isn't it? So P of k plus 1 is true. Therefore, P of n is true, which basically is what you're trying to calculate, or that's basically what you're trying to prove. All right, so basic steps. Let me quickly just summarize what we have done in the video. First, you're going to have a sequence or a series which says that this is equal to something. Right, so in our case 1 plus 2 plus 3 till n is equal to n into n plus 1 by 2. Step 1, show that P of 1 is true. Step 2, show that P of k is also true, in the sense just put n value as k, and once you do it, you are going to get the value. So in step 3, you are going to take P of k plus 1, get the value. After that, you show that P of k plus k plus 1, that means till P of k, then you are going to add the next term k plus 1. Show that this is also equal. Now once you show this is also equal, you have proved P of k plus 1 is true. Hence P of n will also be true. This is the general form in proving mathematical induction. Alright, so from the next video onwards, we'll start solving problems on the same type.